afternoon session. Our first speaker is Abrams from Polytechnica Wrocław, and he will talk about rigidity of topological entropy of Fuchsian boundary maps. Please.
This picture later, but for like one Julio's talk earlier, where in my case, so we can think of it as quotient of the hyperbolic disk by a polygon, and that my talk and his will end, but we do. Of genus G, the most greater than equal to 2, the most.
I'm sorry, we cannot hear you very well. There are a lot of strange sounds and the sound is disappearing.
Okay, is this better?
I don't know. There's like some interference and also the sound disappears. So I don't know if it's the batteries or something.
Checking the microphone. Okay, now there should be no feedback now.
Now it's perfect.
Okay, good. In my setup, instead of using an octagon for genus 2, I'm using a 12-gon for genus 2. And the pictures that I'll have are always for genus 2. So sometimes I'll say out loud numbers like 12 or 24, but actually I mean 8G minus 4 or 16G minus 8, where G is the genus of this surface. The slides will have the expressions with G, but it's just easier for me to say 12-gon instead of 8G minus 4-gon out loud. Adler and Plateau, I'll talk about a few times in this talk. They describe this really nice 8G minus 4-sided polygon. And the notation that I'm going to use throughout today is so capital T with a subscript K is going to be the map that pairs one side of a polygon, side K of a polygon with the other. I don't know. So the other definition that I need to, notation that I need to start with is capital P and capital Q. Almost every single slide in this talk will have a capital P or Q, or maybe a capital A, which I'll say later. And all these is that you take one side of your polygon, label something side 1, and then number the rest of them counterclockwise. You extend side 1 to the boundary of the hyperbolic disk, and we label those endpoints as P1 and Q2. So those are the endpoints of the geodesic containing side 1. All of the other P's and Q's just come from the other sides of the polygon. So there's lots of capital P's and lots of capital Q's. And as I mentioned, capital T is the map that pairs one side of this polygon with another. We're not strictly gluing opposite sides, but you don't really have to worry about what the identifications are. I will point out that all of the indices that I mentioned when I say capital TK or capital PK, they're always mod 12 because these are sides of a polygon, 4 points on a circle. So for example, side 1 is glued to side 7 for genus 2. And this map, capital T2, you can think of it as a map on the disk, gluing sides of the polygon, but mostly we're going to be interested of thinking it as a map on the boundary, on the circle at infinity. So it maps points on the circle to other points on the circle. For example, those endpoints P1 and Q2 that I mentioned earlier, they're mapped to Q8 and P7 respectively. In fact, the inside of this red circle is mapped to the outside of the orange circle, which means if you think about it, that as a map on the circle, T1 takes a relatively small interval between P1 and Q2, and it maps it to a very large interval, going from Q8 all the way around the circle to P7. So if we look at a graph of, well, I switched to T5 for some reason, but for any of these generators, as I'll call them, because they do generate the Fuchsian group, if you look at the part of this graph between P5 and P6 for the map T5, it has a large derivative because it's taking this small interval to a very large interval. Now these generators, T1, T2, up to T12, they're defined on the whole disk and on the whole circle. All of the graphs that I'm going to draw today, like this one on the right, is as a function of arguments. So I have negative pi to pi on the x-axis and negative pi to pi on the y-axis. That's what all of these graphs will look like today. So my circle at infinity is negative pi to pi. And the idea that Bowen-Series had basically was to say, use certain generators of your group on certain intervals of the circle. And so you get this map, which in my notation is f sub p. I don't know if it makes a difference where my hand is. So f sub p is just using a specific generator of the Fuchsian group. So this surface is the hyperbolic disk mod a Fuchsian group, or equivalently mod a polygon. So use a different generator on a different interval of the circle. Here are the definitions just in a concise form. And this map has several nice properties. It's ergodic, it's expanding, it's transitive. It is Markov as well, which I'll talk about more later on. That will be important. And it's been studied actually by several people. So this is called the Bowen-Series boundary map because the first people to write about it were Bowen and Series. But then there's a very nice paper by Adler and Flateau who give a lot more properties and work with one other very closely related map. What we want to do is take this Bowen-Series boundary map and modify it in some ways. And there are two main ways that we could modify this setup. One thing we could do is change the polygon that we're using, which basically means changing within Teichmüller space. So the Teichmüller space of the surface can be thought of as quotienting by different polygons. The other thing we could do is leave the polygon the same and change which intervals we're using the different generators on. So as I mentioned, changing the polygon is equivalent to changing in Teichmüller space. So I guess this slide also actually looks similar to one we saw earlier today of tessellations by a polygon in the hyperbolic disk. For today, we don't really need to worry about this Teichmüller space idea, but this is one change that we could make to the original setup. The other change we could make is to alter the intervals where we use these maps. And so this is really what the main object that I want to talk about today. When I say boundary map, what I mean is this map capital FA, F sub capital A. Capital A bar is a multi-parameter, so it's a list of 12 numbers for genus 2, each in between PK and QK. And the animation that you saw on the title slide was showing changes in these parameters. So this slide's not animated. I'll just go back and forth between these two. This is changing, I guess, A3. A3 is in between P3 and Q3. And so when you change the value of A3, you get a slightly different map on the circle. And these are all what we call boundary maps. There are some particular choices for the parameter capital A that are worth mentioning individually. So one sort of obvious choice is to set all of your A's equal to P. That gives you the original Bowen-Series boundary map. Another choice that sort of makes sense to look at is to set all of these parameters equal to Q, Q1, Q2, Q3. This gives you a map which Adler and Flateau called the backwards Bowen-Series boundary map. So here are some names and some dates, and to go with them, some pictures. So Bowen and Series made this original map. Adler and Flateau looked at, they didn't use this notation, but the way that I'm saying it, they looked at the map f sub p, and they also looked at f sub q. And then my co-authors, I should mention, although it was on the title slide. So this is all joint work with Svetlana Katok and Ilie Ugarcovici. They had the idea of adding these parameters, looking at a whole family of boundary maps. And then as sort of a side project to that, I ended up writing a paper about these extremal parameters, which I'll put the definition back. So an extremal parameter is one where each parameter A is either pk or qk. So that includes the original Bowen-Series boundary map, and the backwards one are examples of extremal parameters in this family. Just as some motivation for why would you want to change the intervals where you're using generators? That seems like maybe a strange thing to look at. But the motivation for this, the reason we started looking at this setup, is if instead of a co-compact Fuchsian group, you used SL2Z, then the quotient of the hyperbolic plane that you get is called the modular surface, and geodesic flow there is very nicely related to continued fractions. If you think about how you make a continued fraction for a number, you're subtracting an integer and then you're taking a reciprocal. So you are using the maps that glue sides of this hyperbolic triangle, or you can think of it as four sides if you split the bottom. You're using the maps that glue sides of a polygon together. You're using those maps on the boundary of the hyperbolic plane. And which intervals you use those maps actually gives you different continued fraction algorithms. So the usual continued fractions, you only do a reciprocal when you have a value between 0 and 1, or for minus continued fractions between -1 and 0. Even as early as the 1880s, Adolf Hurwitz was writing about his versions of continued fractions, which, although he didn't use this language, he was using generators of a Fuchsian group on different intervals of the boundary of hyperbolic space. That's what he was doing. And then there have been much more recent versions with continued fractions, Nakata and Ito and several other authors doing what they call alpha continued fractions. And then my co-authors have some papers where they have 2 parameters instead of just 1. And now in this co-compact case, we have 12 parameters. So that's just why we ended up looking at this and to maybe motivate this as a worthwhile object to study. There are 2 results about entropy. So I feel like I'm stealing from the previous talk. I had Fuchsian groups from Julio's talk, and now I have measure-theoretic and topological entropy from Andrei Bish's talk. But when I was in Vedlevo last time, I presented this orange result about flexibility of measure-theoretic entropy, which was brand new at the time. I'm not going to talk about that result today. I pretty much just have it here to compare and contrast with the result I want to explain today, which is rigidity of topological entropy. So it is kind of surprising that we have these 2 very different results. The flexibility result, so flexibility means that you can, in some sense, get any value for some dynamical property. And it turns out that as you change in Teichmüller space, the measure-theoretic entropy of this boundary map with respect to its smooth invariant probability measure can take any value between 0 and some maximum that depends on the genus. For topological entropy, you can change the polygon, you can change the parameter, and the entropy is never going to change. So the topological entropy is always exactly the same, and that's what I'll prove today. I do want to point out another difference is that the measure-theoretic entropy result in orange is only valid for certain classes of parameters. So it's true for these extremal parameters that I mentioned. It's also true for parameters with short cycles and some other specific classes of parameters, capital A. But we think it's always true, but we can't prove it in general. The rigidity result is really for any parameter you could possibly pick. This animation on the title slide, you could change those parameters to any values you want, and we absolutely know that the topological entropy has this value. I'm sort of cheating by writing the inverse hyperbolic cosine here, because this is just a log formula, and maybe that looks a little bit more like a log. But I like both of these formulas. They're very very short, very simple formulas for entropy, but the proofs are not quite so simple. The proof of this rigidity result has a few steps. The first of which is, we'll just explain that we can deal with regular polygons and not have to worry about other polygons. They won't affect the topological entropy, which to me makes sense. I mean, the polygons, these surfaces are all topologically equivalent. So maybe it's not surprising that topological entropy doesn't depend on changing the polygon. The extremal parameters, as I mentioned, FP is Markov, and actually all of the extremal versions, FQ and any others, are also going to be Markov. And so for a map that's Markov, we have a nice way to calculate the topological entropy as the log of an eigenvalue, the maximal eigenvalue of the transition matrix. So we'll do that, but it's only valid for Markov maps. What we do for non-Markov maps is use a result of Alceda Misterevich, building off some other names who I'll mention later, which says that if you have a map with certain properties, then it's conjugate to a map with constant slope. You can think of like an expanding map, 2x mod 1 or 3x mod 1 has entropy log 2 or log 3 respectively. We're doing something a little bit similar. We're making a map that has constant, it's piecewise linear with a constant slope. And that slope is just going to be e to the entropy. Then the last two steps are just analyzing the map that conjugates our boundary map to a map of constant slope. It has several symmetries, which will be clear in the picture, but I'll also try to say something about how we prove them. And then lastly, we use that to show that the map psi p, so psi is what I'll name this conjugacy, it's designed just to conjugate FP, the original Bowen-Series boundary map, to a map of constant slope. But it turns out that it will conjugate all of this whole family of boundary maps to a map of constant slope, which is pretty nice, actually. It does a lot more than the original theory says that it should be able to do. The most difficult part of this, so the paper that's referenced at the bottom there, about 1/3 of that paper is simply proving one symmetry fact about this conjugation, this conjugating map. That's actually by far the most difficult part of this proof. And so I'll mostly skip it today because otherwise the talk would be too long. But the other steps I'll try to explain. The first step, as I mentioned, is to say that we can always use regular polygons. And basically, this is a result of the Fenchel-Nielsen theorem. So the Fenchel-Nielsen theorem says that in this context, if you have a Fuchsian group and a fundamental polygon that is not regular, you can conjugate everything to the version where you do have a regular polygon. And so for the rest of the talk, I'm just going to use a regular polygon. I'm not going to worry about irregular polygons anymore. When you have a regular fundamental polygon, that helps because you get some other information about these generators, as I call them, these capital TK that map sides together. The isometric circle of TK is going to be exactly the geodesic from PK to QK plus 1, which I had drawn earlier. We also have that all of these points, P1, P2, P3, are all going to be evenly spaced around the circle if your polygon's regular, and Q1, Q2, Q3, up to Q12 are also equally spaced. So I'll use alpha for the space between those. And one more notation, I'll use capital CK for basically the center of that isometric circle. Well, I shouldn't say that. For the midpoint of that interval on the circle. These generators have their own symmetry properties. When you have a regular polygon, they have these nice symmetries, which are really easiest to see in a picture. So lemma A says that all of these generators, T1, T2, et cetera, are translations of each other. Remember that these graphs are on with a circle on the x-axis and a circle on the y-axis. So you're basically looking at a torus and you can translate this. So lemma A is saying that you can translate T6 in blue to get a version of T5, which is in green. Lemma B is saying that each individual boundary map has central symmetry or rotational symmetry. So it's like an odd function, except reflecting through some point other than 0. And you can see that rotational symmetry or central symmetry in this picture as well. Yeah. So for the green one, it's rotating around that point. For the blue one, it's symmetric through that point or this point on the x-axis. Now, I mentioned that the original Bowen-Series map, and in fact, FA for any extremal parameter is Markov. The Markov partition that we're going to use is just using all of the P's and Q's as boundaries of our intervals. Every extremal parameter gives you a boundary map that is Markov with the same Markov partition, but they're each going to have their own transition matrix. So we're using the same Markov partition, the same intervals, but the transition matrix is going to be different for each parameter. And now we're only looking at extremal parameters. In general, the boundary maps are not Markov. But for extremal parameters, they are. We have this Markov partition. And this is just the standard definition of a transition matrix. Proving that this is actually a Markov partition is using the same lemma that I showed very, very briefly on the first slide. Adler and Flateau talk about how this generator maps specific points on the circle. And so if you take the interval from P1 to Q1 and map it under T1 or T2, you get unions of other Markov intervals. The same thing if you take an even index Markov partition interval, so from like Q1 to P2, and you map that, you also get a union of a lot of intervals. So it is a Markov partition. And the transition matrix looks like this for the original Bowen-Series boundary map. Just a couple things to notice here. So there's a very clear difference between the even rows and the odd rows. You can see the even rows have just, the odd rows have just 2 ones, and the even rows have, I think, 17 ones, if I remember correctly, out of 24. You can also see that if I switch back and forth between MP and MQ, you can see that the even number rows don't change. That green highlighted second row is exactly the same. But the odd numbered rows, like the red circle and now this magenta circle as well, those change between the two maps, between the two transition matrices. And the reason for this, if I go back to the Markov partition, is that the different boundary maps for different extremal parameters, they disagree on which generator to use on the interval I1. So FP uses T1 on the interval I1 because for FP, A1 equals P1 and A2 equals P2, etc. If your extremal parameter has A1 equal to Q1, then you're going to use T12 on this first interval I1. For the even numbered intervals, however, all of the boundary maps agree on what generator to use there, because the parameters that we're using, maybe I'll probably have drawn this earlier. So if you have, thank you. So there's a part of your side of your fundamental polygon that goes from pk to qk plus 1. And these parameters are somewhere in this interval. So ak is somewhere in that interval. Ak plus 1 is somewhere in this interval in general. For an extremal parameter, we're saying that AK is exactly PK or exactly QK. So the only difference then is in where you use these generators. So these parameters tell you when the boundary map uses different parameters, when the boundary map uses different generators, And for an extremal parameter, because each AK is either exactly PK or exactly QK, the only thing you're unsure about is this interval between PK and QK. You know here that, for example, if this is T1 and Q1, you know that FA is going to be T1 here for all extremal parameters. You just don't know what's happening between P1 and Q1. That depends on your parameter. But you do know what's happening between Q1 and P1, Q1 and P2 in this case. And that's why the even rows of the transition matrices are the same for all of the different extremal parameters. That's all I'm going to draw. So these transition matrices are the same on the even numbers rows, different on the odd numbered rows. But for all of them, for P and for Q and for any other extremal parameters as well, we can prove that the maximal eigenvalue of this matrix is still going to be the same expression, 4g minus 3 plus the square root of 4g minus 3 squared minus 1, which in the future I'm just going to refer to as lambda rather than reading out that whole expression.
Adam, we cannot hear you now. Do you think maybe the batteries run out?
Microphone. Is this on? Can you hear me?
Yes.
Okay.
Thank you.
Thank you for telling me. Yeah, please do interrupt if there are any technical problems or if there are mathematical questions. Of course, you can always interrupt. So this proof for the spectral radius is really just a game of counting the number of sequences correctly. Using these facts about the transition matrix and the Markov partition, basically each even number symbol can be followed by 17 different symbols. Each odd symbol can only be followed by 2 possible symbols. So that's where we get this equation at the bottom of the current slide. And then playing around more with these equalities, we end up with a linear recurrence relation for the number of admissible words. And anytime you have a linear recurrence relation like this, so you can think sort of like Fibonacci numbers, except instead of 1 and 1, we have 8g minus 6 and -1. You always get this exponential format for your sequence. And then the exponential growth rate of the sequence is exactly the spectral radius of the transition matrix. So we do know for extremal parameters, we have this Markov partition. We know exactly what the topological entropy is in that case. So for extremal parameters, we know for sure the entropy, the topological entropy of the boundary map is log lambda, where lambda is this expression which I said out loud earlier. But this only tells us how to do Markov, how to do extremal parameters. In general, most, there are only countably many parameters that can give us Markov, the Markov property for our boundary maps. So most of these most of the boundary maps in this family are not Markov, and yet somehow our result says that they have the same entropy. What we do for the non-Markov cases, I should also say that we have the eigenvector as well. For the non-Markov cases, we need something completely different to help us figure out what the topological entropy is. And the tool that we use in the non-Markov case is results of Alseda and Measure-theoretic, which really goes back to Perry, basically. So Perry had this method to conjugate a map to a map of constant slope. But in order for Perry's method to work, it had to be continuous, piecewise monotone, topologically transitive, and Markov with positive entropy as well. Then Milner and Thurston extended this to non-Markov maps using kneading theory. Alseda and Measure-theoretic were able to do it for piecewise continuous maps instead of actually continuous maps. So these are the published results and the names that go with them. But as I understand the history of it, there is one more name that deserves to be mentioned here, and that's Felix, because as I understand it, this Alseda-Measure-theoretic paper, the only reason it exists is because Felix wanted to use Milner and Thurston's results for a piecewise continuous map. There was no published result like this, but he asked Measure-theoretic, can you do this for a piecewise continuous map? And Michal said, yeah, I think that should work, but it's not written anywhere. I guess I should write a proof of it. And that's why this Alseda-Measure-theoretic paper exists, which I use very strongly in this result. So even though I'm not citing anything from Felix, I still owe him for being able to prove this result today. What we're using really is the idea that you can conjugate to a map of constant slope. Now, the papers that I mentioned in the bullets are for interval maps. Ours is a circle map, so it's not technically a result that's in any of those papers, but there's nothing new here in this corollary to say that for each parameter, your boundary map can be conjugated to a map of constant slope on the circle. It's going to be locally increasing. It's on the circle, so you can't really require it to be increasing or monotone, but it's locally monotone. And it's unique up to rotation of the circle. For the original results with interval maps, this conjugating homeomorphism is truly unique. In our case, it's unique up to rotation of the circle. So on the next slide, I'm going to show you graphs of the boundary map in blue, which we've seen before, and the map that it conjugates to in red, this map of constant slope. And I'm going to show you this specifically for the original Bowen-Series boundary map FP. Most of what I'm going to say today is about FP, and then at the end we'll show that actually this is enough to tell you it for every map in this family, not just when A equals P. So here's the boundary map. Here's the map that it conjugates to. And this is maybe what you would expect it to look like. So the original boundary map for a regular polygon has these nicely periodic sort of swoop integral-like shapes in the graph. When you conjugate this to a map of constant slope, you just replace all of those with straight line segments. So this picture, we kind of expected this picture to look the way it does. My co-authors and I were kind of surprised when my computer program finally successfully drew the map that conjugates them. It looks like this. So it's a devil's staircase where sort of like a Cantor function where you have continuous but zero derivative almost everywhere. It also, you can see, has a lot of symmetry. So you can think of basically x plus sine of x has the same kind of symmetries that this map has. So it's not periodic exactly, but there's a translation symmetry here, which makes sense for a regular polygon because everything is just repeated 12 times around the circle for a regular 12-gon. There's also this rotational or central symmetry. So if you rotate the graph on the right, I just have a zoomed in portion of the box on the left. And if you rotate this graph around the point C7, C7, you get exactly the same graph. So it's like an odd function, but around some other point. And so we have a proposition that, yes, the map psi actually does have these properties. We do make a couple conventions to help with this. So we're modeling the circle as negative pi to pi, since we're doing arguments on the unit circle. And For convenience, we're going to take one of these centers of the interval from pk to qk plus 1, and we're going to call one of those centers 0. It's the point with argument 0. We're also, for convenience, going to say that the conjugating map fixes that point. Since we're on the circle, this map psi p is unique up to rotation of the circle. So we can choose one value for the function at one point freely, and then the rest of it is going to be unique. With those two assumptions in the first line, we have this proposition. Property 1 is this translation symmetry. Property 2 is that it actually fixes all of those midpoints of intervals. You don't have to turn the lights back on, but I should add CK to this picture. Property 2 says that all of those points CK are fixed. And property 3 is this central symmetry. So alpha is the distance between P1 and P2, but it's also the distance between C1 and C2 and so forth, because everything is on a regular polygon. The translational symmetry of the conjugating map follows pretty easily from the translational symmetry of the generators, which was lemma A that I mentioned earlier for a regular polygon. I'm not going to go read through every piece of this, even though it's only 2 slides. The idea here is we make a map in the very first equation at the top that does the correct thing between P1 and P2, so using the conjugating map psi, and then it just copies and pastes that for around the rest of the circle. We prove that this new map phi does conjugate fp to a map of constant slope, which means this map phi actually is our conjugating map psi. And so yeah, we proved just with some algebra and looking at these relationships between generators carefully, we proved that it is constant slope. And you can read the details in the paper if you're curious, but it's the proof of property 1 is very fast. The proof of property 2 is even faster. That's the whole proof of property 2. So once we have these conventions that we're labeling one of these capital C points as 0, and we know that they're all separated by exactly alpha, that means that all of the capital C's have an argument that's a multiple of alpha. And using property 1, which says that psi of x plus p equals x plus alpha is psi of x, and then adding alpha at the end, that means that once one of those is fixed, the rest of them are fixed. So property 2 comes immediately from property 1, really. Then we have property 3, which takes much more work to prove. As I think I mentioned, about a third of the paper with this result is actually solely devoted to proving property 3. It turned out to be a lot more difficult than we thought it would. It does use the symmetry of the generator. And that was easy to prove, that the individual generators TK are symmetric around CK. And at first, we thought that we could do the proof of property 3 just as quickly, and that it would be a really short paper, maybe too short to publish. But then we realized that that argument was incorrect, and it took many more months to fix it. So I guess the good news from that is it makes it a more substantial result. But you need actually, in order to prove the symmetry of psi, you do need some details about the construction of this conjugating map. I won't go through all of it, but I'll say a little bit about how this is done. So the Bowen-Series boundary map, FP, and what Adler and Floteau call the backwards map, FQ, and in our notation, it's FQ. They are sort of symmetric copies of each other. So if you take negative FP of negative X, that gives you exactly FQ. And you can see in these pictures that one graph is a rotated version of the other. So there is this nice relationship between the boundary maps for the parameter P and the parameter Q. That pretty easily implies that the conjugating maps also have are symmetric versions of each other. In order to get property 3, so property 3 is an equation version of saying that psi P is symmetric around CK. If I take the left-hand side of property 3 and I start trying to compute it and simplify it, I can get it to a form where we have a constant plus psi p of x minus psi q of x. And we want to just have a constant. So we want this red piece in the bottom line to be 0. We want that to go away completely. And it turns out those two terms actually do cancel out. It turns out that the conjugacy for P and the conjugacy for Q are equal. But that was really difficult to prove. Once you have this theorem 2 in the red box, so red means it's difficult to prove. Once you have theorem 2, you very easily get property 3. And once we have property 3, it actually won't be too hard to get our rigidity result. But theorem 2 really was a lot of work to do because the Alceda-Misarevich result is just about one map at a time. It says you have one map, you can conjugate that to a map of constant slope. If you have some other map, okay, it has a completely different conjugacy, a completely different map of constant slope. There's no reason that they should be related at all. In our case, of course, these maps are themselves closely related, so there's a lot more that we can say. But there was nothing automatic here. Proving theorem 2 took a lot of work involving the details of this conjugacy construction, which involves the eigenvectors. I'm not going to go through these slides in detail, but this actually involves Perry's original construction from '66. So that was for Markov maps, which this is. So we could just use Perry's construction, and then you have to get into a lot of symbolic dynamics, looking at the Perry measure in the symbolic space, then looking at the Perry measure or the pullback of this measure to the circle, or well, originally the interval, and for us the circle. That's actually how you define this conjugacy, how you can construct it. And you get a devil's staircase basically because you're changing the value of the conjugacy on smaller and smaller cylinder intervals. This expression for the measure of a cylinder shows up in a few different places in this proof. And it basically comes down to the fact that each interval, this picture, is that each interval on the circle where if you're coding using the Markov partition, you look at the interval where the first several terms are fixed. So you get sort of a cylinder on the interval, on the circle. That actually, the cylinders for P can be decomposed as a union of cylinders for Q. So there is some nice relationship between FP and FQ in terms of the symbolic codings. And in some detail that would take another 50-minute talk to really do in full, we end up proving that psi p and psi q are equal. So I'm just going to jump to that fact, that psi p and psi q are equal. And as I mentioned, that pretty much is what you need in order to say that psi p has central symmetry. So once we know that psi p has central symmetry, we're actually ready to prove the main result, the rigidity of topological entropy. And you'll just have to believe me that the proof of property 3 works. So this result, to remind you, is that well, here I'm stating it for a regular polygon, but we already saw that you could use irregular polygons and it wouldn't really make a difference. For a regular polygon, we have these extra properties of the generator, so I'll prove it for a regular polygon, that any parameters you choose, any values of capital A, you still get the same topological entropy. And the way we prove this is actually pretty short. It's just going to be 3 slides, and that'll be the end of the talk. We look at, well, we have this Bowen-Series boundary map, FP, and we know that it conjugates to a map of constant slope. So we've seen these 2 pictures before. And what I want to do is just focus on one interval between PK and PK plus 1. In the picture at the bottom, I've highlighted between P3 and P4. So we know that the boundary map uses the generator T3 on this interval. And we know that the map of constant slope, well, has constant slope on that interval, that that's one piece of the piecewise linear function as well, or the map of constant slope. If we ignore everything other than that interval, we think, well, okay, on the left, the blue picture, this is showing a little piece of the generator T3, which inside the disks maps side 3 to side, whatever side it's glued to, but on the boundary is just a map on the circle. And T3 can be defined on the whole entire circle. So I can take T3 and do that as a map on the circle. We saw a picture like this earlier, but a priori, we have no idea what it looks like if you conjugate that, because this map psi p was designed to conjugate FP. It wasn't designed to conjugate T3. So there's no reason that this conjugated version of the generator should behave nicely outside of the interval from P3 to P4, or the corresponding interval, which I'm doing with primes here. It turns out, though, that it does behave very nicely. So if you conjugate the generator with the conjugacy that's designed for the whole boundary map, what you actually get is a piecewise linear map on the circle. It's very, very nicely behaved, which I don't know if this is surprising or not. Maybe these look pretty similar, but it's a bit strange when you realize that the map I'm conjugating with is this bumpy staircase, devil's staircase. And yet somehow it takes a really nice Mobius transformation and conjugates it to a map that is truly piecewise linear. So the red function on the right, it has slope lambda on one interval and slope lambda inverse on the other interval. So really nice map of the circle. And yet the conjugacy is this strange thing with 12 sort of repeated bumps in it. So how do I know that? Because at first, the general theory doesn't tell you what the conjugated version of T3 should be outside of this little interval. How do we know what it does anywhere else? Well, I'm going to take this red picture on the right and just highlight that interval. So here we have basically the same drawing that I had on the chalkboard earlier. So part with psi applied to all of those points. But so we have the interval from p prime k to pk plus 1 prime. The prime just means that I've applied psi p to those points. And we know that the conjugated version of T3 is linear on that interval because it's designed to be. I'm claiming that we can extend that section where it's linear just a little bit further out to qk plus 1 prime. And the reason I know we can do this is using the symmetry. So the conjugating map is symmetric around CK. The generator is symmetric around TK. So this composition is also symmetric around CK, which means I can take this red interval and reflect it around CK. So I've made the tick mark for CK longer at the bottom, and I'm just going to take this red interval, reflect it around CK to get this gold interval. And now if I know the map is linear on the red interval, and I know it's linear on the gold interval, well, it's linear on the whole thing. It's linear on their union, which is exactly from PK to QK plus 1. So actually it's linear on this slightly longer interval. And why does it help to have a slightly longer interval? Well, our boundary map with parameters is using parameters that are somewhere between PK, AK is somewhere between PK and QK, AK plus 1 is somewhere between PK plus 1 and QK plus 1. So that's why we need to extend this linearity out to QK plus 1. We need to know that this whole green interval that I've shown now and the endpoints of this interval are adjustable because these are the parameters in our family of boundary maps. No matter how I adjust those endpoints a little bit, this green interval is still going to be inside PK to QK plus 1 because that's sort of the maximum possible range that these two parameters could give you. And now we know that our conjugated generator, so TK conjugated by psi p, is linear on this interval. And the boundary map FA, well, all it does is use TK on those types of intervals. So this is a little strange because we're using the boundary map with the general parameter A, and we're conjugating it with the map that was specifically designed to conjugate psi p. But what we've basically shown here is that psi p and psi q and psi a for any a at all, they're all the same conjugating map, which doesn't happen in the general theory about conjugation to constant slope, but it does in our very specific setup. And that's really the end of the proof. We've conjugated our boundary map to a map with constant slope lambda. So its entropy is log lambda. And all we really needed was the symmetry of this conjugating map, this staircase shape, to finish off the proof. So I'll just remind you of the two results, the flexibility of measure-theoretic entropy, and now I've shown basically the proof of the rigidity of topological entropy. And that's it. That's a summary of how we did that. And I'll say that the topological entropy is strictly larger than measure-theoretic entropy. That I think is a good place to stop. So, thank you.
Yeah, thank you for the nice talk. And any questions?
Yes, if I may.
Yes.
So to maybe one remark about this result with Luis Salceda, maybe you should add the name of Jaume Libre there, because our proof is really a not so big modification of the proof that we gave in our book of 3 authors for continuous maps. So simply we took that proof and changed some details so that the proof fits to the piecewise continuous case.
Okay.
And the second thing is kind of question. Okay, there is a phenomenon that people call entropy locking for maps of piecewise linear maps with 2 pieces but discontinuous for interval maps, and then for some 1 parameter family on the whole interval of parameters the entropy is the same. And with David Cosper we found a kind of quite simple proof of that using elementary geometry. And I wonder, maybe here you can find another proof which could be simpler if you try to use, say, projective geometry.
I don't know. We tried some simpler proofs that we actually thought were successful at first and then realized they weren't, but they didn't involve projective geometry. I actually had an idea just this past weekend that instead of FP and FQ, there might be different parameters that could use the same idea in the proof I laid out here, but take the part I skipped, this really difficult symbolic dynamics relationship, and make that shorter. But I decided I didn't want to try to figure that out in the 3 days before my talk. So yeah, maybe there is a better way to prove this, and that would be nice if there were.
Okay, and any other questions? Yes.
Yes, you're conjugating map between the linear and pieces Möbius case. So of course this is a devil's staircase. So it's always interesting to look at the local regularity properties. So for instance, try computing the Hölder exponent. Likely to be Hölder, but have you tried to check? And in any case, it would be nice to try to compute this. Does it depend only on G, or maybe it's more complicated? Yeah.
I don't know for sure. I expect that it is Hölder. I know that the conjugation between this map H from the Fenchel-Nielsen theorem, I know that that is Hölder. And under some very specific facts about, it's Hölder, but not Lipschitz, unless your Fuchsian group has some very specific properties. So I know that there also are some results about that conjugating map between the irregular polygon and the regular polygon. We didn't try to investigate whether our conjugation psi to constant slope is Hölder or not, but I would guess that it is.
Yes, and any other questions? Okay, then let us thank our speakers. The next talk will resume at 4.